We are Team 8, and our senior project was the vacuum bleeder for Lenger Racing. The team consists of Jacob Boovy, Parmveer Tumber, Mitchell Hundle, Braden Chittenden, and Joshua Suzio. The sponsor contact was Drew Siegersma, and the faculty advisor was Dr. Olshay. The purpose of this project was to create a machine that improves the consistency, efficiency, and cleanliness of the current manual shock assembly and fluid filling process. This was done by making a machine that receives empty, assembled shocks and fills them with fluid, removing air from the shock during said process. In the images below are a few of the steps of the current process where new shocks are received in their disassembled form, partially put together and partially filled with fluid. A vacuum pump is then used to remove any trapped air in the shock or in its oil. Finally, the shock is assembled further while more fluid is added as needed. As for specifications, the vacuum bleeder was to be constructed within a budget of $5,000 and be of a reasonable tabletop size. It was to be capable of interfacing with shocks that range in bore diameter of from 2 inches to 4.5 inches and a stroke length of 6 inches up to 22 inches. To properly fill the shocks, the system was to be capable of supplying oil at pressures of up to 160 psi, and it was to be capable of interfacing with up to 2 identical shocks simultaneously. On the right are 2 images of the vacuum bleeder. The oil fill port can be seen on top of the machine, and on the front of the machine are the HMI, e-stop push button, status light, shock hookups, and a window to allow the operator to monitor the vacuum reservoir fluid level during a cycle. Now with the door open, the vacuum bleeder makes use of pressurized air and an injection tank filled with fluid to push said fluid to the shocks. A vacuum pump and reservoir are used to remove air from the shocks and oil. A one-way valve is used to relieve pressure from the shocks back through the injection tank when said tank is depressurized. Controlling these systems is a PLC and HMI combined unit, which monitor machine status through sensors and actuate valves to control the process. First, a shock was attached to one of the hoses and the corresponding manual hand valve was opened. Then the correct HMI parameters for that shock must be set up. For the shock being demonstrated, this is a 3.5-inch bore, 18-inch stroke with bypasses present on the shock body. The vacuum bleeder is then ready to switch into auto mode and start the machine cycle. The vacuum bleeder has a pre-check screen to double-check all system settings prior to starting. The initial injection for this shock takes about 4 minutes, where oil is injected into the shock, forcing the shaft to extend. For this initial injection, after the shaft is extended, about another minute is spent pressurizing the air that was in the shock prior to starting. This will allow for easier removal of said air in the subsequent steps. While running, the manual screen can be switched to monitor pressures and fluid readings as well as the status of valves in the vacuum pump. Here can be seen at the end of the injection cycle, the system is waiting for the flow rate to diminish sufficiently to determine that the injection is complete, where the system will relieve pressure of the shock and tank, and the air that was previously pressurized in the shock is now forced out. During vacuum cycles, negative pressure is used to remove air from the shock and fluid. Doing so also forces the shaft of the shock to retract. This displaces fluid and air near the top of the body of the shock through the hoses and into the vacuum reservoir. The vacuum reservoir fluid level can be seen during vacuum cycles thanks to the window on the front of the enclosure and a light that switches on during vacuum cycles. The vacuum reservoir not only acts as a space to build vacuum, but it also prevents the vacuum pump from ingesting fluid, as doing so could damage the pump. It is essential that the shock is oriented in a manner so that the interfacing point of the shock is at the highest point on the body, so that air has the least resistant path out of the shock. The vacuum bleeder performs 3 injecting, venting, and vacuuming sequences, after which the shock shaft is extended using a 4th injection and venting of the pressure, where a pop-up on the screen prompts the user to evaluate the shock. Here, a semi-clear hose can be observed to see if there's any fluid present in the hose that has just left the shock. The shock can be manually compressed, forcing the fluid at the interface port out of the shock. If there's any air remaining in the shock, it will leave the shock when it's compressed, and the user can request an additional vacuum and injection if they deem it necessary. If the bleed is deemed sufficient, however, the user can select Complete Cycle, where the shock will be refilled and the process complete. After a final injection, and once the system has returned to atmospheric pressure, the process is complete and the freshly bled shock can be removed. The vacuum bleeder for Lenger racing introduces a standardized bleed process that reduces the effort and time required from the operator while also limiting the waste of shock oil. This system satisfies the necessary requirements of the project and provides Lenger a tool to use and build off of for future use.